Hello, welcome to this video of the classics. We've done a bunch of stuff the previous videos. I added some questions, so today we're covering this question, the sixth. So we consider r to the power n, so r times r, with n being an integer, non-zero, and the canonical scalar product that I note like this. So you put the first thing here, the second thing here. It's the scalar product. We note S n plus plus of R, the set of symmetric matrices with real values and with strictly positive eigenvalues. It's kind of complicated, but we'll get through. And may A being a matrix of that set. So and I call S, big S, the unit sphere. So if x is a vector of r to the power n, then its norm equals 1. So now we want to calculate the minimum with x in the unit sphere of a times x scalar x times a minus 1, the inverse of a x scalar x. That's kind of complicated, but we'll get through. So at first we can notice that we have the sphere unit, so the norms of the vector will be 1, which is kind of cool. Let's see that. I need to scroll down. Okay, 6. Okay. So I note U, the endomorphism associated with A, so it's diagonalizable because we've assumed it in the question because it's a symmetric matrix with only a real symmetric matrix, so it's diagonalizable. So we get 4 values of A in range 1n, U of fi, so f is it's a base, so it's the base that I call. Oh well, I could have just put it right here. So I call the f and the base of eigenvalues. So if you do UFI, you get lambda IFI, with lambda I being the spectrum of the matrix A, which is also the spectrum of the endomorphism U. So you get that by the definition, well, by property of the scalar product, you get that AX scalar x is equal to UX scalar x, and same here. So we call x inside the sphere to be equals to the sum of the xi fi. So I now write this scalar product, so it's equals to this. Then by property of the endomorphism, if you do U, the fact that you have the U, you'll get this, because it's the F is the orthonormal base of eigenvalues. So there will just be a lambda that will appear. So you'll get this. So now we have a problem because to calculate the scalar product, we have fi and fi here, but it's not the same sum. So for I and j in range 1 n squared, if I and j are different, the scalar product is 0 because it's an orthonormal base, so the vectors are orthogonal, so can't like have a scalar product that isn't 0. And if it's the same vector means that the norm of fi is 1 because we are on the on an orthonormal base. Okay, so now we can put from this into a single sum, because the terms that are not fi will cancel out because they will be equal to 0. So you get this. Then you can factorize by lambda I xi and then xi here by a bilinearity of the scalar product. So you get this, and actually this is equal to 1. So you get this. Shit, there is a fucking storm out there, so it's kinda noisy. So we do the same with the inverse application. Since it's an inverse application, we can just do the same thing, but instead of having lambda I, we have 1 over lambda I, because the inverse application is just the same thing with the inverse eigenvalues. So we get the same thing here. So we do the product and we get this. So now the problem is that, well, obviously there is one step here. We just express this as a squared and a square here, so we get this. So the problem here is that we don't know what to do with this. It's a product of sums, and usually it's really bad. So we use the Cauchy-Schwarz inequality. So we get this equation, this inequality, sorry. So this is this, but here the scalar product is the square root of the sum of each of the vectors. So we get this, and we have our ai squared that is here, and our bi squared that is here, and we replace in the formula. So I just put this part here and this part here. And the square root of lambda I and 1 over square root of lambda I will cancel out. So you get the sum of the absolute value of xi squared. But since it's real, I can just remove the absolute value in the next step since it's squared. And this is actually as we've seen earlier, this product. So we have this. And actually this sum is equal to 1 because we are on the unit sphere. I forgot to write it. Since x is in S. Okay, so we have this inequality here. So we know that it's superior or equal to 1, but we don't know yet if it reaches 1. So the goal will be to find a value so that it equals to 1, and that will be the minimum because we know that it's superior or equal to 1. So I take any vector of the family of the base. So I do u of the application u of one of the vector of the base. Scalar, the same vector, it doesn't really matter. So I take f1, and we get this from the application u, and f1 scalar f1 is equal to 1, so we get lambda 1. So I do the same thing with the inverse application, and we get here that this thing applied in f1 is equal to lambda 1 over lambda 1, that is equal to 1. So there exists vector so that this equals to 1, but we know that it cannot be below 1, so the minimum is equal to 1. So that's it for this question. I hope you enjoyed it, And thanks for watching. If you have any question, feel free to ask them in the comment. And bye.